up, and we just wanted to save time for that. I don't know if you can see that. So then, see it? We could bring it over. That's Steve.
Hey, Steve, Larry, Scott. I've heard you guys 10 times, but I've never seen you. So what's that? I'm sorry. No, we're good.
Is that just the aluminum in there, or do you have the polymer?
The aluminum
only. Before you add the polymer, can we take it off and show then?
Okay.
All right, he's taken some water. He's added a few milliliters of aluminum sulfate to the frac water, and he's mixing it right now. And in a few minutes, after he's stirred it up, and I'll bring it over closer to the camera, and you can see it. It's already started to take the water, and you'll see things starting to float in the water now. He's also going to take some of the production water and do that test as well. Or you're just going to use that beaker? And we'll do that at a separate time.
Yeah, ready.
Is that ready? Can I show them on the...
Howdy. 4 minutes?
Okay,
let me get 1 more minute.
Yeah, wait till the minute. All right, so you stir that for 4 minutes. I don't know if you can see it on the camera, but right now there's a lot of... That water is actually now pretty clear, but there's all the little yellow things floating in it.
Half a minute.
By the way, this is Pepe, our polymer chemist.
Jose, Pepe. He goes by Jose.
Pepe. Doctor.
Hey, just to let you all know, we're doctors here. I know these lab coats on. Don't be fooled by this, all right? That's right. Hey, nobody's talking to you.
I want to take it and show them what it looks like, so they can actually see it floating around. Can I take that? I don't know if you can. Can you see this? The floating?
Can you see the floating particles in there?
Okay, now what we're going to do is add the actual polymer, and that'll really start to create the block.
If you'll notice too, there's on the top of that beaker, there's a black ring on the top of it. This water that I brought, there's no oil been removed from it. So that piece of equipment that we're talking about using, removing the oil first, will make this job 10 times easier.
Now, can they see that? Okay, now he's getting ready to add the polymer.
Smile.
And how much are you going to add?
3 milliliters.
He's going to add 3 milliliters to that size of the sample.
They're going to centrifuge.
And we actually took your water and filtered it because it's just makes it too time consuming.
Yeah, we're going to take it.
I mean, if in the field somebody didn't want the oil taken out, wanted us to treat that, so we could do that. But I think the process might be long.
Well, everybody that I've talked to said, hey, if you can get the oil out of it, great.
Well, it makes our life easier too. And time is money. So if somebody wants you to clean it without it, you can agree to do that. Set it up. Just know the process might take a little bit longer and a little bit more complex. And we can tell you what that will be. But we've never treated anything that heavy yet. Right. So we can't tell you exactly today how much more you need, but we'll know after today.
Okay.
We were using more of the water that you I'm sorry? Yes, you don't have to. We can clean it either way. But if you take the oil out in the field, then the amount of polymers that you need and the amount of time, obviously it'll be faster. And we're not talking hours longer, but and significant. But we could use maybe twice as much of the polymer on that water as we did on the water after the oils were taken out. And the process, instead of taking, I think right now they could do a batch in about 8 minutes once the polymers are mixed. So maybe the oil takes you 10 minutes or 15 minutes. I don't really know that final answer yet, but it'll be something like that. It's not significantly different, and it's not a showstopper. Just know that it takes a little bit longer and a little bit more volume. And so what he's doing after he's added polymer is going to let it mix for about 8 minutes. Usually, has it already been 8 minutes?
Yes.
Is it ready?
Ready. I'm going to start another 2 minutes to clean up.
Show them.
Okay, if you let it sit now, that stuff will start to settle out. You can see it floating in there, and it'll start to settle on its own. What we can do is filter it, and that's what we plan to do in the field. Either run it through a hydrocyclone.
Paul, why don't you do it over here where they can see it?
Yeah, let's filter it.
You need a filter. Get a coffee filter. 2 coffee filters, Scott.
Actually, maybe it'd be better to filter it into a smaller one, so it'll be higher up and there's more to see.
This one?
Yeah.
Here, right here. This is clean.
This one? That's clean.
This one's clean. Sí, porque necesitamos hacer las pruebas inmediatamente. Más bien que esas son las pruebas que necesitamos comenzar para que se den una idea. Entonces, si las pruebas que hicieron un modo por el lado, pero bien para dar resultados. Si pueden, su sistema no está en 23 también, en 26 también. En 26 pueden discutir con las gracias. This is before.
Okay, we're going to filter that through just a coffee filter, and then what I'm going to do is make a measurement on the turbidity. I have a little meter. I'll take a sample of it, and we'll run it through. The water that before it's been treated, the meter won't even read. We get no reading. It's too high. And so I'll make a measurement of that water.
Before or that's before? This is before and after. This is after.
Can you see it? Can you see that, Steve?
Pour some in here. Yeah, you can see the difference. Bring it up close, can you see close?
Don't worry about that.
Show them the top. No, show them this top.
Show them the filter.
Show them the filter.
Don't. Watch my computer.
Okay, let's pour some into here.
What will you do with the stuff on the filter, Paul?
Well, that's going to be remember we talked about for 600 barrels a day, you're going to have about 19 pounds of that stuff after a day. That's the stuff that'll spin off the hydrocyclone.
Yeah. That's the stuff that's depending on its how hazardous it is. Depending on how hazardous. No, gotta go for the dump. Hazardous waste
It's on the floor, Paul, by your left foot.
Might be able to burn that quick. I think it's fine, but it won't have much oil in it. You've already taken it.
Yeah, we might be able to burn it too.
Do you want to bring your turbidity over here, Paul, or you could show?
It works on batteries, so let me in.
Well, we'll figure that out. That's down the road.
Just gonna put that in there.
It's measuring the clarity of the water.
9. So it went from over 1,000 to 9. Seven. What was the standard? EPA wants for drinking water generally under 1. But once again, keep in mind, turbidity is not a measure of how clean the water is. It's how clear it is. It kind of tells you how much is floating in the water. This water still has a very, very high salinity content. And probably the reason why the numbers are not around 1, because if you look at it, it almost looks like tap water. But I think the salt level is so high in the water that it's causing the light that run through it to scatter a little bit. So that's probably why it's even as high as it is. But that probably has a pretty high TDS level. So that was again, that's pretty clear water. It's the white. Where is it looking? Like that. Yeah, it does look like drinking water. It does. Essentially, what we're measuring with turbidity is how much light if you shine a light through the sample, how much of it gets scattered instead of going straight through. And the amount that it gets scattered is proportional to how many things that are floating in the water. So obviously, the lower, the better. Right, but remember this process, the polymer doesn't take out things that are dissolved in the water, which is like the salts. That's going to be what our new water process will take the salt out. This just takes out iron sulfide, oil, anything else that's floating in the water.
Okay.
And leaves you with a pure brine water.
Does it tell us what the TDS is?
I have a TDS member, but it's higher. It's above 100,000.
It is.
But my meter won't read it. So that's.
Yeah, we need to be around 6 to 10,000. But that's going to be done. There's all kinds of things these guys have that can really manufacture the water to what the customer wants. And that's what we've seen with Enduring and Devon and Pioneer and Apache. Everybody wants different water. Everybody wants a different quality of water. They want the sodium chlorides to be different. Last year in June, they wanted 0 or less than 3,000 of sodium chloride, and 3 weeks later, 20,000 was perfect because the fresh water was closing up and swelling up the clay formations down underneath, And what happens when they do that is it shuts all that fracking that you just did. It just eliminated it. These guys have.
Well, we have a desalination system that we're going to use.
They have another process
but
too.
We're not
with the,
ready
with
for
the ammonia.
commercial yet.
Yeah.
But there are other ways to get the TDS down if that's all you want. See, our process is actually going to take the TDS down to almost under 100. I mean, very, very low. Almost like distilled water.
Right.
I think we got it down as low as 40 at one point when it was over 100,000 to start with. But we're not commercially ready yet. We're still 4, 5, 6 months away. Maybe more.
So we need, what he's saying is we need more money, guys. So you need to get off this call right now and go find some.
Or we need to find, well, there might be some commercial that if you only need to get it down to 20,000 parts per million.
I think 20,000 parts per million would be perfect.
There are other things out there that will do that.
And like I said, there's every oil company is different, and then you have to also consider the formation that you're in and the type of water, the drilling fluids that you're using, the gels that are going down hole. Those gels are coming back out. So there's tons of different. Did I lose you, Steve? I lost you, Larry. I lost Larry. I lost Larry. Okay, well, Larry's picture's gone. There, now you're back. Did you go to the bathroom? We don't want to see that, thank you. But we're going to spend next couple of days at the ranch and talk about all the different possibilities, and then all the other stuff that's coming from this too, guys. There's Doug and Scott are extremely well connected with a lot of people in this country, especially Texas, and we're going to sit down today and tomorrow and kind of figure out what we need to do as far as the company and where we need to be. So yes, I'll let you kind of explain it too, Scott, what we were talking about as far as the ammonium and
that's Paul. We can talk about.
Okay.
Talking about the ammonium recapture.
Right.
Well, our distillation system that we use uses a process called forward osmosis, and forward osmosis is most people think of reverse osmosis. And what you do with the reverse osmosis is take the salt water and apply a lot of pressure to it, and that forces the water through a membrane, leaving the salt behind. And that takes a lot of energy. And when the salt level gets as high as the water we're seeing, the membranes just fail altogether. They work mainly for seawater or less, which is about 30 to 40,000 parts per million. We're talking 100,000 parts per million. So what we did is we do forward osmosis, and that's essentially a natural process where water wants to go through a membrane from low concentration to high naturally. So if you take water on one side and salt water on the other, water will go through the membrane into the salt water to dilute it. Nature wants the level on both sides to be as even as it can get.
What he's talking about is clean water and dirty water.
Right.
One attracts to the other.
Well, I started out with salt just because it's easy to see.
Right.
What we're going to do is make the dirty water that we want to clean appear cleaner than our clean water side. And the way we do that is we add to the clean water side water that has ammonia and CO2 in it at a very high concentration. It's higher concentration of ammonia and CO2 than the things that are in the dirty water. Therefore, to Mother Nature, it says, that's the dirtier side, so I'm going to leave the dirty water, go through the membrane, and go into this ammonia solution. And the reason we chose ammonia and CO2 is they boil off at very low temperature. So we can heat them, and now the ammonia and CO2 turn into a gas and leave the water, and you're left with just fresh water.
And we can recapture that gas.
Yes, we've demonstrated all of that, even at a flux level of about, with a scalable system, about 1,000 gallons per day. Now we know we can stack units to get to any level you want. What we haven't demonstrated is the ability to take that ammonia that we distill off, ammonia CO2, collect it, and remake up that solution. If you don't do that, your ammonia and CO2 costs will be too high to have a commercial profit.
Correct.
Now, it's not doing anything that hasn't been done. I mean, gas recapture systems are done all the time on oil refineries. We just need to actually build one to do it. So I don't see a big issue in doing it. It's just that we